Okay, today we're going to talk about linear independence. Last time we talked about span, and span is one of the main concepts in linear algebra, and linear independence is the other. I mean, I think it's fair to say that these are the two most important critical concepts to really master in linear algebra, which is span and linear independence. And they will show up like every day, and so it's important to take the time to really understand these concepts. So what is linear independence? Oops. Oh my. Hold on. Okay. Well, we've seen this concept a little bit before, just without the words. So if you have a line in R2, say, we've seen, for instance, that the span of the vector 1, 2 is the same as the span of, well, first of all, it's the span of, say, 3, 6, because you can take a third of 3, 6 and get 1, 2, right? And you can take 3 of 1, 2 and get 3, 6. And so you get the same line, but it's the span of 3, 6 and 0. No, that's not right. It's the span of 3, 6 and -2, -4. You know, I mean, you could even throw in, 4, 8 and 6, 12. The span of the vector 1, 2 is the same as the span of these four vectors, because they all lie on the same line. However, if you're going to describe that line, right, so what's this line? Here's the vector 1, 2. Okay, it's this line. You want to describe it in terms of one vector. It's the span of, you take one vector that's on the line, and it's the span of that one vector. Even though it's true, this line is the span of, these four vectors, nobody would really say that. And so there's some redundancy in giving this list of vectors, because by saying the span of 3, 6, you're already looking at this whole line. Right? And so this notion that this list of vectors is in some way redundant, this list is redundant, you can say what the span is by using one vector instead of four. That leads to the notion of linear independence. So we would say that this set of four vectors is linearly dependent. And now we're going to go to the definition of linear independence. And there's a couple ways to kind of say what it means for a set of vectors to be linearly independent. And I'm going to define it in a different way than is typical. There's really two ways of looking at it, and I'll use the more common definition later. Okay, they turn out to be equivalent mathematically. So we're describing the same set of vectors, but usually this is not how linear independence or dependence is defined. But I think it's more intuitive and easy to understand. So what's the definition of linear independence? Well, a set is... Okay, let's get to the definition. Before we get to the definition... Okay, I'll erase this. Recall, so to provide some context, recall that if you have a set of vectors, v1 through vk, and these are all in the same Rn, right? So it's not like v1 is an R2 and v2 is an R3. Okay, so if this is a subset of Rn, then the zero vector is a linear combination of v1 through vk. How can you write the zero vector as a linear combination of v1 through vk? No matter what v1 through vk are. You can take 0 v1 plus ... plus 0 vk, right? Okay. But depending on the set, this might be the only way you can do it. So I'll now come to the definition. I'm going to define linear dependence, and then I'll say that a set is linearly independent if it's not linearly dependent. Okay. So the set S, which is v1 through vk, is called linearly dependent if at least one of the vectors in the set is a linear combination of the others. Okay? That's what linearly dependent set means. And if the set is, if S is not linearly dependent, well, then it's called independent. We call S linearly independent. So linearly independent means, i.e., so what would be, so if linearly dependent means at least one of the vectors is a linear combination of the others, which is what it means, what would not that mean? That would mean, so it's linearly independent if none of the vectors in S is a linear combination of the others. If no vector in S is a linear combination of the others. So let's look at an example. Let's say I have the vector, let's say that S is the set 1, 3, 2, 6. Is this linearly independent or dependent? Now it has to be one or the other. You can't have one that's, neither. It either is linearly dependent or it's linearly, I forgot what I just said. It's either linearly dependent or linearly independent. So which one is this one? Can I write one of the vectors in S as a linear combination of the others? Yes. S is linearly dependent because we can express one vector as a linear combination of others. Okay, we should say which one. Well, in this case, it's either one, but we can express certainly 2, 6 as 2 times 1, 3. Right? And we could also have done 1, 3 is 1/2 of the vector 2, 6. Okay? And notice that this is an example of a redundant set of vectors, right? Because if you look at the span of S, not S, but if you look at the span, that's the line through 1, 3. And notice that this is redundant because you wouldn't say the span of 1, 3, and 2, 6, though mathematically it's correct, but you span a line, and so you could have only just used one vector. All right, let's look at another example. So how about 1, 3, 2, okay, let's just change the 6 to 5. Now what about this? Well, neither of these is a linear combination of the others, right? So is linearly independent because, remember, when you have two vectors, how can 2, 5 be a linear combination of 1, 3? Well, when you have a linear combination of one vector, that just means a scalar multiple, right? So because 2, 5 is not a scalar multiple of 1, 3, and 1, 3 is not a scalar multiple of 2, 5. So neither vector is a linear combination of the others. Now in this case, you could say that that's a bit, did you really have to write all that? If 2, 5 is not a scalar multiple of 1, 3, then of course 1, 3 is not a scalar multiple of 2, 5. However, you could say something like, let's say you have the set 1, 3, 5, 2, 4, 6, 0, 0, 0. Now, this is a subset of R3 because the vectors have 3 components. Is this linearly independent or dependent? You want to take a moment? You can pause if you want, but I'm about to go over the answer. This set is linearly okay, I think time's up. The answer is linearly dependent. Now, how can I write one of the vectors as a linear combination of the others? It's because I can write 0, 0, 0 as a linear combination of the others. I can write it as how? 0, 1, 3, 5 plus 0, 2, 4, 6. Now notice that you can't write 2, 4, 6 as a linear combination of 1, 3, 5 and 0, 0, 0. And you also can't write 1, 3, 5 as a linear combination of 2, 4, 6 and 0, 0, 0. However, in this case, 0, 0, 0, it was possible to write it as a linear combination of the others, and that was the only vector that could have been written as a linear combination of the others. So just because you can write one vector as a linear combination of the others doesn't mean that you can write the other vectors as a linear combination of the others. That makes sense. Okay. And more generally, right, you can do this thing no matter what the vectors were. If these two vectors, 1, 3, 5, and 2, 4, 6, were different vectors in R3, you could still do the same thing, right? So let's just make a note. So similarly, if S is a set of vectors in, say, Rn, and S contains the 0 vector, S is linearly dependent. Because you can write 0 as 0 times a different vector. And even if S only contained a zero vector, that would be linearly dependent still, because you can oh shoot. Well, yes. I mean, even if S is just the set, say 0, 0, 0, you can write so I think there's an issue with this zero vector. No, you can't write 0, 0, 0 as 2, 0, 0. I mean, you can write 0, 0, 0 as 2, 0, 0, 0, but then you could have done the same thing for all the other vectors, right? So, okay, so maybe an exception has to be made for the set containing just 0, 0, 0. So maybe I should be more precise and say, if S is a set of vectors in Rn and S contains 0 and at least one non-zero vector, then S is linearly it's linearly dependent. I have to think about the concept of what happens if S is just the zero vector. By the other definition I have in mind, it would be linearly dependent. So, okay, one thing I can say is we define, because there's really no good notion of linear independence when you just have the zero vector. We'll define the set just consisting of the zero vector as linearly dependent. We consider just the set consisting of the zero vector as linearly dependent. I'll get to why in a second video next time. But hopefully this gives you some intuition about linear independence and linearly dependent, linearly independent vectors. And notice that if you have, these two vectors, 1, 3, and 2, 5, these are not redundant, right? I mean, the span is a plane in R2. You can't somehow remove one of the vectors and maintain the same span. Okay, we'll come back to linear independence next time.